Math has always had a very close relationship with music. According to Pythagoras, there is geometry in the humming of the strings, there is music in the spacing of the spheres. Pythagoras himself ran countless experiments when it came to music, especially those concerning frequency. First off, it's important to define what frequency is. Frequency is a number of occurrences with a time reference. For example, a blender's frequency may be 15 rotations every 1 second. In music, we define frequency with the unit hertz. 1 hertz is equal to 1 revolution per second. So for the case of the blender, the frequency of the blender would be 15 hertz. It's really important to recognize what frequency is and what hertz are in music because that's one of the ways that we are able to label a sound. It's also important to define what units volume is measured in. The volume of a sound is basically the strength of vibrations of a sound wave. There are two units in which volume is measured, which includes pascals and decibels. The one crucial to the understanding of music and its theory are decibels. Decibels are logarithmic units which are used to describe a ratio between, in our case, both sound pressure and volume. It can be found using 10 log the quantity P2 over P1 equals dB, where the quantity P2 over P1 is the ratio of the intensity of the same sound played at different volumes. Sound, in physics, is a vibration that moves in the form of waves. The number of oscillations that a sound wave completes in 1 second can also be represented as 1 hertz. For each frequency, there is a note that corresponds to it. For instance, the frequency of the note A would be 440 Hz. The frequency for the note G would be roughly 391.995 Hz. Next, octaves are an integral part when it comes to understanding music in the least bit. Basically, an octave is a series of 8 notes that take up space between and including 2 notes, with the highest note being double the frequency of the lowest note. If we take the note A at 440 Hz and double the frequency, the note would still be labeled as A and it would sound the same, but the pitch would be higher. With this knowledge, we can now turn back to Pythagoras and his experiments. Basically, what Pythagoras did was he experimented with a rope and focused on the sound it made based on how many sections that it was subdivided into. If the rope is sectioned into 2 parts, the note produced will be the exact same if it was strummed as one section, but it will be an octave higher. When Pythagoras divided the rope into 3 sections and strummed it, the note was different from when the rope was divided in half or not divided at all. Pythagoras continued subdividing the rope into sections and combined some of the sounds together to create scales. To summarize Pythagoras' findings, it basically stated that the sound and pitch of a string is directly proportional to its length. During the course of the year, we learned about variation during Unit 2. We can determine the frequency of a string that has a length C based on another string with a frequency A and the length B. This is because the length of a string varies inversely as the frequency of its vibrations. For instance, if we had a harp string that was 8 inches long and it vibrated at a frequency of 640 Hz, we could find the frequency of a string that was, say, 20 inches. Using the formula for inverse variation, which is y equals k over x, we should first make 8 equal to k over 640 and then solve for k. Once we find k, which is 5,112, we could then set up the final equation to find the frequency of a 20-inch string. 20 equals 5,120 over x and then solve for x. X should end up equaling 256. The frequency of a string 20 inches long is 256 hertz, which ends up being a middle C. Now that we understand the length of a string and how it affects the sound it produces, it's time to talk about the instruments themselves, specifically stringed instruments. Cellos, violins, violas, etc. use the exact same method Pythagoras used in order to be played. By pressing down at a certain point on a string, you can control its pitch by controlling how long it is. The farther down you move the point where you press, the higher the note becomes, because the length of the string that's vibrating becomes smaller. The reason harps are so large, with so many strings, is because of the conclusions that Pythagoras came to. Harps have strings of varying lengths because it's difficult to press down on the harp strings in order to change its pitch, so it has different length strings in order to account for that. In conclusion, while music and math may not seem closely related at all on paper, the truth is that mathematicians and musicians have been collaborating since ancient times.